Welcome to the Cosmic Pie Podcast, episode 21, season 3. I'm your host, Wayne Barkhouse, and here with me,
Robert Moore. Nice to meet everybody.
So we are broadcasting live, hopefully, from the University of the campus of North Dakota.
Yep.
Make some fine adjustments, Robert. Why? Do you want to tell people what happened lately?
Oh, Lordy. Nothing but technical issues. We finally got our IT department in here to look at it, and they made the determination that it needed a whole new computer. So I've spent most of the past couple of days working on getting things set up. So hopefully this will go off without a hitch because it's a completely new setup. So
it's test of the new system.
yeah.
We do have a chat feature that's running, so if you have any questions or comments, hopefully the chat feature works. So is anyone out there that's actually listening right now, and if you just put in a hi in the chat, and we'll see if we can pick that up, just to test that.
And if I can stop kicking the new computer.
Yeah. Oh, it's in the way of your feet now, is it?
Yeah, it's in the way of my feet, or my feet are in the way of it or something.
Okay,
You know?
well, hopefully that'll work out. Now, the other thing to mention is we are on Spotify, so if you want to watch these recordings later, you don't have the time or the ability to see them while we're broadcasting live, we do upload them there. And to start things off, today is July the 1st. Do you know what July 1st is?
Canada Day, isn't it?
Canada Day, so happy Canada Day to all my Canadian family and friends out there. So we do have some comments in the chat.
Everybody.
Thank you, Brian and Wanda, for sending those in, so we know the chat feature is working. We can read it. That's helpful. So far, so good.
Yeah.
And we need to knock on wood. You ready? There.
Yeah.
Could use the table that would vibrate it.
Bad Rob.
Okay, and if things work out well today, then we're going to do a little surprise next podcast.
Right.
And one of the things
gonna
we're thinking about doing is to
Have one of us wandering around campus.
do a roaming reporter type of situation, right?
And we're thinking of doing that because we've got some other things, if that works, that we're going to try to pull off. So
Yeah, so we'll kind of see what that leads in that case. Anyways, today we're going to start off. Oh, we should do a disclaimer too. We can't
we should
forget
do that.
You want to do
Okay.
the duties on that one?
And as usual, the opinions and everything expressed in the podcast are those of myself and Wayne, not the Department of Physics and Astrophysics at UND, the College of Arts and Sciences, or the university itself. We're it. So.
Yes. Okay, so let's start off with our first news item.
Okay. Where's my cursor? There it is. All right. Bam.
Oh, so everyone should be able to see this.
Yeah.
So this is an update on the Nancy Grace Roman Space Telescope. Now, just to give you some history behind here, so on the right you see an image of Nancy Roman, and she's with a gentleman, so she's seated, and there's somebody standing over looking at what she's pointing out to a model. Do you know who that person is, Robert?
He looks very familiar, so I'm thinking it might be Mr. Armstrong.
Very close.
Buzz?
Buzz.
It's Buzz? Okay.
Buzz Aldrin. So that's the second man to walk on the moon in Apollo 11, 1969, July the 20th, when they landed on the moon. So Nancy Grace Roman actually started with NASA in the late 1950s. In fact, she joined NASA, let's say, in April, if I'm not mistaken, of 1959. So she was there very early on.
Yeah.
And she became the head astronomer for NASA. NASA
okay.
interest early on was to do some space astronomy, so that's not unusual. And the fact that it's a brand new agency getting involved in launching equipment in space, eventually launching humans in space. And one of the things NASA knew that they would have to have experts in was astrophysics and astronomy.
Mm-hmm.
And so
Makes sense.
it makes sense, yeah. And so Nancy Roman was able to then fill that important niche and work her way up the ranks in NASA and become basically what today we refer to, or most people, as the mother of the Hubble Space Telescope. She had a lot to do with the implementation and the funding and getting it launched and everything else with the Hubble Space Telescope. And that's, of course, become one of our most successful space telescopes in modern eras, arguably. Obviously, the James Webb is sort of a replacement in some sense. To the Hubble. But that was our first real good space observatory.
Absolutely.
Even though you think about it, boy, didn't it take a while to get up there.
It did, and it took a while for it to get to work. I mean, it was delayed on its launch, and then on top of that, there was the problem initially with its optical system. that made everything blurry because it had been mispolished. And so then they had to do all those refitting missions to get it correct, its vision corrected. I was a kid and remember all that. So Hubble itself was a good proof of concept, but it was also fraught with, this is how can we correct what we are. So, yeah.
Yeah, so anyways, it's amazing what people can do when they put their minds to it and got the support. And that's important because what this slide is all about, which is the part on the left, is the fact that the Nancy Grace Roman Space Telescope, and there's a long story which we'll get into in a second of where this ultimately had come from, this telescope. You can see it had just passed one of its major vibrational tests. Okay. So it's something that NASA plans to launch. The launch date, as you see there, would be in October of 26 or maybe till May of 27. That's kind of the contract with the Falcon Heavy right now. So it's probably going to be launched in that window. If you look at the size of the telescopes, you can see the mirror. When you look down at the mirror, like this top left on the left side image there, it's about 2.4 meters in diameter, which is about the size of the Hubble Space Telescope.
Okay.
So it's not like we're going from the Hubble size to something much larger like the James Webb Space Telescope. And the reason for that is an interesting story here, is this telescope was given to NASA by the National Reconnaissance Office.
Okay.
Several years ago.
Okay.
At the time, they were developing space telescopes not to look up at the sky, but look down at the Earth, to spy on other countries, of course. Yeah. And the thing there, this is going back a couple decades, was that ideally there would be a space shuttle that would launch out of the Kennedy Space Center and another space shuttle that would launch out of Edwards Air Force Base in California.
I forgot they did have plans on 2 lab
and that
sites
was a military-controlled enterprise. So it was the military that was spending their money, as far as I know, at least a large part of it, to have a launch pad set up then for the space shuttle on the West Coast. And the idea would be they would launch all of their payloads, their military satellites, with their equivalent of the shuttle. So the shuttle cargo bay is limited in terms of its diameter. And if you didn't have fold-up mirrors developed properly, then a fixed mirror like the one that you see here could be no larger than about 2.4 meters in diameter. And that's what set
I was about to say, that's the cargo bay. Yeah.
That's what set the limit for the Hubble Space Telescope, why it wasn't larger, because it had to fit inside the cargo bay of the space shuttle. And at the beginning, the idea was you'd go up maybe every 10 years with the Hubble. With the space shuttle, you'd put the Hubble in the cargo bay, you close up the cargo bay doors, you bring the shuttle back, you'd refit, maybe re-illuminize, repair anything that was damaged, put a new generation equipment on board, send the whole thing back up in space on the shuttle again. And you could just do this repeatedly. So, and in some sense, the Hubble Space Telescope would be around almost forever in that sense, right? You get tired of it, right? And so that never happened. I think it was related to the shuttle had a lot of problems during its lifetime. Some of those problems included the brake system. So they had a lot of trouble with the brakes and slowing this thing down when it coasted to glide to a landing, and like at Kennedy Space Center. And when they had a heavy payload, they didn't want to take the chance. So that's sometimes occasionally, if you remember the history of this shuttle program, sometimes they would land at Edwards, where they have the long runway, the dry riverbed. Dry lake bed, I should say, and they would land there. So if they had really heavy payloads, they would land there and not have to use the brakes as much as let it sort of coast to a stop. And that basically there was a limit put on how heavy or how massive a payload would be to bring it back. And I think they decided at NASA that maybe we shouldn't bring the Hubble Space Telescope. It's just too massive to bring it back and run.
Which is unfortunate because it could have done with some updated optics and CCDs and electronics.
Yeah, for sure.
Onboard computers. And
I mean, Hubble's on the verge of going. I mean, it's on its last gyro. I think if one more gyro goes, you won't be able to point it accurately to anything. And so essentially it's over with at that point. So there was plans, Jared Isaacman, the one that was nominated in the beginning to be NASA's new administrator, then that was removed by the Trump administration. His goal before Trump became president, Jared had mentioned that he would like to take up, based on his own money, get NASA to go up to the Hubble Space Telescope and try to repair the thing, outfit it with new gyros and stuff. And in fact, I think NASA did a study of it along with SpaceX to see if it was doable. Maybe you could go up in a Dragon capsule, have a docking module on it, do a spacewalk, and do the repairs. And I don't think I didn't hear the true report of the final say in all of this.
Right.
But I think it was implied somehow that NASA didn't think that that was a good idea for whatever reason. I'll leave it at that because I don't know the in and outs about it.
Right.
And so it wasn't approved.
Well,
I think it's still hanging out there as a possible thing that could happen.
Right. Well,
who
it's like a building. There comes a point where it costs more to refit it and keep it going than it does just to tear it down and put a new building
that's
in.
it. And you hate to do that.
You do hate to do that, but there comes a point where it's much more financially feasible to just put a new one up there. Oh, wait a minute. That's what it looks like this was trying to do.
Well, it's interesting, right? It's like someone gives you a telescope, you have to do some work to it. You have to build the instrumentation. Mm-hmm. The advantage of this over the Hubble is not in terms of the aperture, but in terms of the field of view. It was designed with an optic system so it could see over a wider swath of the sky at any single image.
Right.
So the field of view of the telescope is 0.28 square degrees. Now you might say, what is that, right? Well, to comparison, it's 100 times the field of view of the Hubble Space Telescope.
Right.
So if you think of Hubble looking down drinking straws, right, where this telescope is like us looking around, it's almost like that difference, right?
Right.
So if you want to cover a much larger area of the sky in a reasonable amount of time, then this is the telescope that you would need to use.
Yeah,
so
I mean, 0.28, a quarter of a square degree is a pretty large field of view for a 2.4 meter telescope.
Yeah, so that's about the size of the full moon.
Right.
Right, because you can get 4 full moons in 1 square degree. Because the full moon is about a half a square degree in dimension on one side, right?
Yeah.
So then you get 4 of them in 1 square degree. So this is about the size of the full moon, as for comparison's sake. So that's really good. That makes it worth spending money on to gear it up so that you can send it into space.
Absolutely.
Now, we don't have the shuttle, so that's why you got to send it in some other way, like an unmanned rocket, which is like the Falcon Heavy. So that was the whole situation with that. And you got to have a large enough body at the top, payload bay, the payload shroud, right?
Yeah.
So that you can contain the payload and cover it up with the clamshell, like stuff that you have, essentially, for lack of better words. So that was doable.
It would definitely have to take a Dragon or a Falcon Heavy.
Yeah. So that'll be interesting. Now the problem. Let's say a little bit more about this. So it's undergoing all of these tests. The shaking tests that it went through, the vibrations, all of the environment or conditions that it would undergo during its launch to make sure it can withstand all of these things and not get broke and not function once you get it up there. It's going to as you can see there, the L2 position.
Right.
So
that's Earth trailing?
No, so that's behind the Earth relative to the Sun and the Earth itself.
Okay.
It's the same spot where the James Webb Space Telescope is.
Oh, okay.
Right? So it's kind of going around at the same rate, you see, but maintaining roughly that fixed distance away from the Earth. So that's that parking, that very stable, gravitational potential stable position.
That's what all the L points, the Lagrangian points are.
Yes. So it's going to be there, and there's a lot of other spacecraft there. Like I said, James Webb was just put there a couple of years ago.
And I thought they were trying. That's why I was surprised, because I thought they were trying to limit how much they put there.
Yeah, this one they want there.
Okay.
So be it.
Who am I to argue?
Yeah, so it's going to. No one has an ownership on that. It'd be interesting. Do you get to the point where it becomes now it's a large space, large volume of space.
Yeah.
So you don't have to worry about it. It's probably more of a problem is everybody using the same frequency transmitting your data at the same time. You probably don't. You want to avoid that, right?
Absolutely.
But anyways,
yeah.
So there's lots of room there, but the main problem. So there's a neat telescope. Is it groundbreaking? Well, large field of view and good optics is the latest stuff that you can make that they're making for cameras and so on.
Right.
It's going to do what type of science is going to do? What anything else is going to do? Exploration in dark matter and dark energy and all of this stuff. But so all the other telescopes, if you read the science papers for them or what they're going to do when they start operating. But this one is on the chopping block, and that's the main thing I wanted to note.
Yeah, that's what's in big green letters.
Yeah, this project was pulled by the current proposed federal budget for NASA.
Okay.
And I can see why it's on the chopping block. If something got to go, this is almost redundant. You could make an argument. I could see somebody saying, look, you have a lot of capability in the Hubble, a lot of capability in the James Webb Space Telescope, a lot of capability in a lot of ground-based telescopes. Why do you need even this one? It's nice to have if you had an unlimited budget or you had lots of money or you didn't owe $36+ trillion.
Right.
At some point, the ramifications of being in debt, right, is starting to hit. I think that's what's going on now. You know, if you're in a hole, the first thing they tell you to stop doing is digging, right?
Right.
So you don't go any further down. And I think that's what everything is starting to hit the fan now, I think. We'll see, right? In terms of this debt. People argue, well, half or most of the money is owed to us, and it's not just fancy bookkeeping that's going on here. It's not really we're in that much. But then who knows? All right, I don't know the ins and outs of all that stuff. I don't think anyone really does. But I know we have a problem.
I think that's the problem. The real problem is nobody really understands.
All I know is if we did our books the way the government does, we'd be in jail, right, or something, right? So, or had to declare bankruptcy many times over.
I had a lot of friends of mine who were accounting majors, and when I was doing my undergrad, and they'd try to explain some of the stuff they were doing, and I got to admit, you know, I'm pretty good with math, but when you're telling me you can do the same problem 5 different ways and get 5 different answers depending on who you're talking to, there's a problem. You know.
Yeah. Thankfully, science doesn't operate that way.
Thankfully.
So we'll see what happens. Obviously, it's a proposed budget. It's not been passed yet, but who knows if it'll actually be launched or if we'll put it on mothballs and you got to wait a few more years. I don't know.
I was about to say, at least with equipment like this, you can tear out all the electronics out of it, put it in a locker, and hold it indefinitely till the Hubble falls or something like that goes
maybe
on,
this will
and
be
then
the
put it up.
Yeah, well, maybe then that's the justification. The Hubble is no longer functioning. We had to dump it in the Pacific Ocean, so let's put this up as a direct replacement of the Hubble.
Right.
Maybe that's the argument that you can make and allocate some more money towards that end. But is it going to cost more money than not launching it on schedule? Yeah, it always does because it always costs money to store this stuff and everything.
Right.
So, yeah, it's going to cost more money, but, you know, that's
probably less
the way
than going ahead and
things-
putting it up there when we've got something doing much the same job.
Yeah.
I could see the point. I was
Yeah,
a little
that's what I'm
disappointed
saying.
when I saw that, but I can see the point.
Well, if you had a choice, let's say you're the head guy at NASA, it's your job to cut so many billions of dollars. Which programs you're going to cut? When every single one of them, you're going to cause layoffs or decrease the amount of science that you're going to get back, right, to the agency. But your job is to cut something, Robert, so what do you cut?
Yeah.
That's the answer, right?
Right.
So,
No, I agree.
Yeah.
And like we're saying, I can see this one being one of the ones that they say, hey, do we really need this?
Yeah.
And the answer is, at this moment, no.
Well, the National Reconnaissance Office, if they wouldn't have gave NASA, I think there were 2 spacecraft or telescopes initially.
Okay.
And I think they accepted both of them and then gutted one of them to parts for the other one.
Right.
Or they turned down one. But they accepted one of them ultimately. So if the NRO wouldn't have gave NASA any space telescopes, they wouldn't have went to the trouble of
building
this and figuring the mirror and,
Yeah.
and doing all that. They wouldn't have just had it, right? It wouldn't have been there.
Right.
So you could always argue from that point of view, I guess.
Okay.
Now, speaking about space telescopes, here's an interesting study that just came out recently. It's an image, actually it's a compound image. It's an image taken by both the James Webb Space Telescope. This is sort of the orange light that you see there.
Okay.
And James Webb, of course, is an infrared, mainly sensitive telescope. So these are observations that were taken by MIRA. And the other thing that you'll see there is sort of the blue disc-like structure. And in the center, you see that star symbol with sort of a dashed circle on the outside of it. So the host star, which is TWA-7, that star is about 111 light years away. So it's not in our backyard, but it's pretty close.
It's close enough.
That star has been subtracted from the image because the star is just so bright compared to anything that's around it, like planets, that you got to get rid of that host star somehow to be able to see what's around it. So the image of the star then has been manipulated in such a way that the light from the star has been subtracted. So it would normally occupy where you see that black sort of disk in the center, okay, where that star is there, that's symbol. But notice the blue disk-like feature that surrounds it.
I was going to ask about that because it looks kind of like an artifact.
That is so that's an image taken with the Very Large Telescope down in Chile,
Okay.
and that's run by the European Southern Observatory, and that disk is real. That's a planetary disk. So there's a debris or dust disk.
So this is a
surrounding
young
that star.
star because all evidence to the contrary, that type of thing is gone within about 100 million to 140 million years.
And that blob of light that you see the green arrow pointed to, that's TWA-7b. That is an exoplanet.
Nice.
It's about the mass of Saturn, so it's about 100 times the mass of our Earth. So you can see it so well in the infrared once that host star is subtracted.
Once you subtract
it's
the
so
host star.
obvious.
And I'm impressed at the gas and the dust being imaged to that extent because holy cow.
Yeah, and this is the first direct good image of an exoplanet taken by the James Webb Space Telescope. And there'll be many more. JWST is looking at a lot of stuff, has taken a lot of observations and being processed and analyzed. So you will see a lot more come out in the next several months to a year or so. But this is a real beautiful, clear separation from the exoplanet to the sun itself.
Right.
So if people wonder, are there really planets going around other stars? How do you know? Like, I've heard that they tug on them and you see this tug, but that's an indirect way. Well, here's a direct way. You imaged it. Is there somebody in your backyard? I don't know, but I got a picture of them trying to scale my fence. So obviously there is. So so having a direct image is really good in that sense if you want direct proof.
Yeah.
No ambiguity whatsoever. Now, you do notice another sort of orangey blob.
Was going to ask about that.
That is just an unrelated background star. Has nothing to do with this star and its planets or planet.
Okay.
So this is totally different. So, yeah, this is a real cool image. So just lead you... Say, number one, the advantage of having a telescope in space to work at the diffraction limit, essentially, of the instrument. Mm-hmm. The other one, to have a large aperture so that you can look at really high resolution. The other thing, to have the instrumentation, and this is like the ground-based telescope, that can, as well as space-based, that can occult or block the light from the host star, allowing you to see the much, much fainter light near the edge of the star to pick up things like this. So it's a really good sort of interplay between telescopes, instrumentations, and sort of analysis techniques that allow you to have the developed software to do this sort of stuff.
Because, I'm looking at things. One thing I'm missing here is a scale. So what's the separation between that planet and its host star, TWA-7?
Right.
Some other questions I have are things, what was the analysis process so that I know how much in that disk is artifact and how much of it is potentially legitimate. That it's part of the circumstellar disk, I'll buy, but other things I'm interested in, it looks like there's a denser region of that disk right around the orbit of the planet. What's going on there?
If you look carefully, you could almost see it's cleared out some of the debris disk, right? So which would make sense. A planet is going to clear out its orbit around it, and you can almost see that in this image.
I would really like to know the estimated age of this star, because that would be really neat.
Yeah, anyway. So we expect more of this to come along. So
absolutely.
If we get some nice images like this, we'll definitely share it with everybody.
Yeah.
Yeah. The other thing I want to talk about today.
Okay.
Is
I heard about there being a nanosecond pulse that nobody could explain for a while.
Yeah, that's what this is.
Okay.
That's what this is. So it's the resurrection of the dead. A satellite, it was a couple of them that were launched in the early 60s by NASA. This in particular is known as the Relay 2 satellite. Now, the image you see there on the far right is actually a Relay 1, but they're identical as far as I know.
Okay.
And I couldn't get a good image taken of Relay 2. I guess they took one of Relay 1 and said, okay, that's it. And there's like the like sort of mock-up of it in the Air and Space Museum in Washington, D.C. and so on. Anyway, so the Relay 2 satellite, you could see solar panels all over it.
Yeah.
Get it from the name, what it was designed to do. Relay signals, telecommunications signals, television, and so on.
Yeah.
Back in, mid-1960s. So it was launched in 64. So that's, roughly 60, 61 years ago. And it died in 1967. And it's in this orbit, right? So the orbit is high enough that you don't have to worry about it coming back to Earth. Okay, so it's not like in a low Earth orbit, a couple thousand kilometers up or something like that, or like 3,000
okay.
or something.
So yeah,
It's going to be up there for a long time.
It takes some really serious solar activity to puff the atmosphere out to that altitude.
Yeah, it's going to be up there for a while.
It's going to be
right?
there. Yeah.
Yeah, it's one of those ideas. So everyone kind of forgot about the satellite. So last year, and that's the paper that you see here, which was published on June 13th of this year. It's not that long ago, a couple weeks ago. Back in 2024, there was a signal that was picked up by the ASCAP array. Now, that's the Australian array that's being designed for part of the Square Kilometer Array project. So radio astronomers have wanted a huge array. So what an array is, for those who don't know, is if you take signals from multiple radio dishes and tie them all together, it acts in some respect as a giant radio dish, at least from the point of view of resolution.
Right.
And the amount of surface area you get is just the sum of all the surface areas of the individual dishes in terms of how faint you can go in terms of radio signals being picked up.
It's our good friend interferometry again.
Yeah.
Except at radio waves, it's easier to do because you don't have to have that nanoscale precision, nanometer scale precision in where the beam lengths are, or how long the beam paths are. With radio telescopes, radio waves, you just need to have a timestamp down to like the 10th of a second.
So the idea was they wanted to, if you like, construct a large interferometer array of multiple hundreds of radio dishes, all add together, spread over an area of 1 square kilometer.
That's going to give you pretty good resolution and pretty good amplitude capability as well.
Yes, so that would be a fantastic. The stuff you could see in detail at radio wavelengths would be just, should I say it? Out of this world.
Out of this world, astronomical.
Far out, man. Anyway, so the project has worth a lot of money. There's a lot of jobs in constructing these radio antennas, as you can imagine, hundreds of millions of dollars, and if not $1 billion. But there was a little bit of, as far as I know, I could be wrong on this, but there was a disagreement on where to locate it.
There always is.
And it came down to two major or primary sites, one in Africa, one in Australia.
Okay.
And ultimately what they decided to do is split the project in two. Part of it would be in Australia and part of it would be in Africa. So you combine the signals on two separate continents. Just everything on one continent.
Yeah.
Don't ask. It's all politics, I'm sure.
Oh, absolutely.
So we won't get into that, but it's whatever it is, right? As long as you build the thing, I guess that's the idea, right? Rather than not building it at all. So part of the array, a small part of it is built already in Australia. Some of it's being built and then now in Africa is available. And so the Australian part of the Square Kilometer Array is this ASCAP, A-S-K-A-P. Okay. And they've been, if you got telescopes that are available, why not use them? No sense sitting waiting around till you add more and more to it. Use what you got and test out the equipment and so on and so forth. Absolutely. So they've been doing that. So they make observations. And one of the observations that they made last year was they picked up a blip, and by a blip I mean a 1 nanosecond duration signal.
Yeah,
coming
that's
from
what I was looking at the abstract there.
Coming from a certain location in space. Okay, now the signal itself was less than 1/30 of a nanosecond in width.
30 nanoseconds in width and 300 kilojanskis. So that is a ridiculously tiny blip.
Yeah. So it's a signal that was picked up by the array in Australia.
It's a testament to how precise and what the resolution of this telescope system is.
Well, yeah, what a good test on this.
Yeah, because that's a nothing signal.
And the question is, though, where does it come from? It's so weak. Maybe it's cosmological distances. Could be billions of light years away. Yeah. In fact, there has been short burst radio signals that people have picked up.
Right.
And trying to understand where they come from. Are they associated with supernova, exploding stars, or where pulsars or magnetars, highly magnetic pulsars?
Collisions of black holes.
Where are they coming from,
right.
these bursts of radio waves of such short duration? This one had, if you read through the paper, this one had a little bit of an unusual type of signal. Okay, so it stood out away from the normal or average properties of these short radial bursts that you see. And what they figured out, which is amazing, that it actually came from a location in space that's coincident with the Relay 2 satellite.
Let's see. Some new physics or a dead satellite? A supposedly dead satellite. I'm going to go with the supposedly dead satellite.
Yeah, so this dead satellite should not be giving off any radio signals. Mm-hmm. And the other thing, if it did, it would be kind of useless if it was only like 30 nanoseconds in length, right? I mean, who's going to, so there's something wrong. So there's something odd about this. And what they think it is, they don't know for sure, but it could have been like electric discharge will give off a radio signal.
Right.
And that's the case. All you have to do is during a lightning storm, turn on a radio station on the AM dial, let's say in your car radio.
On AM.
It has to be AM, not FM.
Right.
And if you listen, you'll hear the static that's caused by the release of radio
crackle,
photons from the lightning discharge, right? You'll be able to pick that up with your radio. So maybe that's what it is, some kind of a stat. Now, it's close enough that it can still interact with the ions, the ionized particles in the very upper atmosphere, right? So there could be stuff there, very thin, diluted plasma of some type that it interacts with. Maybe it takes a long time to build up a charge, and then it occurs, and maybe it's reoccurring, who knows?
Right.
So maybe it happens every so often. You just didn't have the sensitivity, right? And looking in the right location at the right time to pick up the sudden flash of the radio signal from the satellite. And maybe it happens with other satellites, too, that are similar in construction and similar orbits. And who knows? I'm sure people will do a lot of follow-up to see if that's the case or not. So we think it's related to that. It's not all of a sudden the satellite came back from the dead somehow, which makes a better story, of course.
It's back from the dead.
It'd be good because NASA would really get its money's worth if the satellite started working again after being dead since '67. So I wonder if that's vacuum tubes that would turn on. I don't think so.
I was about to say, it may just be that it still had a trickle of signal, because back then they didn't just shut things down like they do now. So maybe it had a trickle. That's what I was thinking. It had a trickle signal that we just now got machines, devices that are sensitive enough to pick it up.
Yeah, my view would be that it's probably because in the mid-'60s, this thing was probably designed in '62.
Yeah,
to
it's
be launched in '64. No, it's transistors.
Is it transistors?
Yeah, early transistor diodes and stuff. But the thing is, they didn't know the extent of the radiation environment around the Earth in them days as well as we know today. So maybe it didn't have the proper shielding that we would have in modern satellites.
Right.
And so back then, you could end up with this buildup of static discharge on the surface of the satellite, where today that would never occur because we've taken ways of mitigating that sort of process, right? So our satellites wouldn't undergo that today, but certainly the older satellites, would have that issue.
No, that makes sense, and it's more plausible than my idea. So,
well, you have metal that's circulating in the Earth's magnetic field.
It's going to build up charge.
So charges are going to move around, right?
Yeah.
It's going to happen.
And when charges move, they give off photons.
Yeah, and Maxwell's equations. Right?
Maxwell's equations.
Yeah, can't get around it. Okay.
Some of the best proven, closest to proven theories that are out there.
Yeah, well, electromagnetic, if you go down that rabbit hole a little bit, quantum electrodynamics sums all of the electricity and magnetism phenomena, and we know, different values theoretically to like the 12th or 15th or 18th decimal point, whatever the number is, I forget now.
Yeah.
So it's a theory that if it's not the right answer, it's a huge, very, very, very close approximation to the real thing to get such accuracy in numbers that you predict theoretically and then compare to experiment.
Right.
So seems like we're down the right track with that kind of stuff. Right?
Absolutely. Yeah. So,
Now, the next story I want to show you is related to the bullet cluster. Well, it is the bullet cluster, I should say, but it's related to this whole business of dark matter. So we can get into a little bit of this today to kind of give people an idea, if they've never heard of the bullet cluster before, what this is all about. The bullet cluster is actually two clusters. Mm-hmm. And what we think has happened in the distant past is that two clusters were moved towards each other. merged, went through each other, and are now going out the other side. So they pass through each other. Okay. Now, what you see here superimposed is an image taken by the James Webb Space Telescope. Okay. And then with that, the color coding, the pinkish color, if you like, that's from observations taken with the Chandra X-ray Observatory. So they're X-ray observations. And in the X-ray, or if you have an X-ray telescope, what you're seeing is hot gas.
I was about to say, so that's hot gas.
That's hot gas. So wherever you see hot gas, is going to be, you're going to pick it up with the pink color that you see there. Associate the two. The blue color is where the mass, the gravitational mass of the clusters are located. And notice there's two clumps. Conveniently, God put circles, dashed circles around each of the clumps. So there's one on the right and one on the left. So notice there's the blue clump on the right, one on the left. So that's where most of the gravitational mass is of those two separate clusters. Now, the one you see on the right side, the smaller of the two circles, that used to be on the left side and pass through roughly the center of the other cluster, now going away from each other, their own separate ways.
Okay.
Two ships in the night, except they interact. And what happened here was that each of these clusters, before they pass through each other, contain their own amount of hot gas.
Okay.
Now, that hot gas, which you can see because it emits X-rays, when those two clusters started merging together on their first pass through, they only pass through each other, the hot gas interacts because it fills up a huge volume of space. There's no way getting around it.
And we know that from other observations of other clusters.
Yes. And when you have two hot gas that run into each other, you get these shock fronts that appear. In fact, the name the bullet cluster comes from the bow-like feature that you see there inside of that smaller circle on the right. You see that in the pink where you have that sort of, if you like...
it's a bow shock.
It's a bow shock, exactly.
Yeah.
So
it's the front end, if you've been in a boat, it's that front point of the wave that's being pushed in front of you.
Yeah, so you think of a shock wave or something propagating at a fast speed through the atmosphere, you see that shock front. So that's what you see there as that hot gas is interacting. So in some sense, it's stalled, as you notice, in between the two circles to a degree. Because it can't go through each other. There's a resistance. It can't pass through. It's like you running into somebody else. You know, you do the funny thing at sports events sometimes, like at hockey games, where people dress up as in big rubber suits and they run into each other.
Right.
You know, to keep everyone's attention during the intermission time or something, right? So you can't pass through somebody because you keep running into their midsection.
Right.
So that's just kind of going on with the gas here. And that, like I said, is detected in X-ray, so we can observe that. What you see is the blue light is where the mass of the cluster is, a gravitational mass in the form of things that give off optical light like stars, in other words, galaxies.
Right.
So the galaxies themselves, the average distance between them is such that they do pass through each other. So you have two clusters pass through each other. It's rare for the galaxies to merge and collide with each other in the stars because they're relatively small in terms of their apparent diameters relative to the average distances between the galaxies. So there is some interaction, some merging that occurs, but it's very rare. It's not predominant. It's not like every single galaxy would collide with, you know, every other galaxy that's in the other cluster when they pass through each other.
That's where that analogy of two people running in together breaks down.
Exactly.
Yeah.
It's like you had two house flies that head towards each other. What's the chance of two house flies making a direct collision?
Very small.
Very small, because the sizes of the house flies are tiny relative to the space between them. And of course, forgetting about the other effect that they have brains and probably can avoid each other anyways, right? But assuming they couldn't, right? It's very rare you see two houseflies collide in midair. Okay, that's why it's hard to shoot a missile with a missile if you think about the military and things that have happened lately in the world, right? It's very difficult to do that. So the dark matter itself, right, does not interact except by gravity with other things in the universe, as far as we know. So the dark matter itself is like the galaxies that we see. They can pass through each other. In fact, the circles that you see, the small on the right, the larger on the left, most of that gravitational mass, by about 85%, is not in the form of things we can see. It's actually in the form of dark matter.
Right.
And dark matter will cause the shape of things to be distorted because it curves space in its vicinity.
And I was about to comment, there's all those red squiggles, especially over in that left-hand side. That's gravitational lensing.
That's gravitational lensing. And that gravitational lensing can put an approximation on the total amount of mass that you find in each of these clusters.
Right.
So most of the mass, then, we know it's there because of the gravitational lensing effect. And the dark matter, which we think makes up the majority of these systems like this, by far, then, pass through each other when those clusters pass through each other early on in their histories. Remember, it's the hot gas that can't get through. It fills up such a huge volume of space, it runs into each other, creating these shock fronts.
Right.
So by the fact that you can note the amount of lensing, the curvature, the shearing, and distortion of the optical image of the galaxies in the individual clusters, tells you how much matter that there should be there to give rise to that effect.
And then you can look at what you can see visibly in all wavelengths, X-ray to radio.
Then you know there's got to be dark matter there.
Right.
It's not bound up into that hot gas that emits X-rays because it wouldn't have passed through each other. It would be trapped in the center like where most of the pinkish light is located.
Right.
Where that
and
shock front is
instead we're
there.
seeing all these curves, red squiggles
Right. So if
outside.
dark matter didn't exist, then you wouldn't have seen these lensing effect. It would be mostly in the hot gas, the mass of these
Right.
clusters, and therefore trapped in that X-ray emitting region.
Yep. And there is a good deal of it in that.
There's a good deal in it. It's like
that
roughly
region.
15% of the mass of a cluster
Yeah.
is in the form of hot gas, but it's ordinary matter.
Right.
It radiates energy in the form of X-rays. It's ordinary matter. It's plasma, it has an electric charge, hence it radiates light. But
yeah.
the light is, because of the high temperature, tens of millions of degrees, it radiates at X-ray wavelengths.
Yeah. I'm going to mention something there. When astronomers talk about temperature, you got to remember that it's the average kinetic energy of a statement about the average kinetic energy of the particles. So the particles are moving as if they were that many millions of degrees. But, you know, if you were in there, you might be hit by one particle over the course of 100 years.
Yes, that's why in physics, when we talk about the temperature of something, you never say, what's the temperature of a single particle like an electron? It's a meaningless
question.
Because by definition, temperature means the average motion of things, of an ensemble, a collection of objects.
Right.
So you could happily talk about, for example, what is the average temperature of a bag of electrons, or like a bag of marbles is the analogy I'm thinking, right?
Right.
And it's just the average kinetic energy of motion of those particles.
Right.
So you'd never say, what's the temperature of a single electron? That doesn't make sense. So that's what we're getting at here. And so it's the motion. But if you look at the density of the particles, how many of these particles exist per cubic centimeter volume of space, then that's the effect that can cause damage. If that density is high and you walk in this 10 million Kelvin gas, you'd be done for, right? You're eliminated immediately if you want to think of it that way.
But I'm imagining from what I've heard,
disintegration.
Yeah, the density there is probably on the order of maybe one particle per cubic meter.
Yeah, it's extremely low for sure.
Because
extremely
I know
low.
the inner solar system, intra-solar system, it's like 3 protons per cubic meter.
Yeah, very, very low, which is why, as you mentioned, you could step out in that because it's so rarefied, which is the correct word to describe that. You're not going to do bodily harm to yourself you know, instantaneously type of thing, right?
Right. If you were exposed to it for long enough, there would be problems.
Yeah, for sure.
Especially with all the X-ray photons
now
that are being flying
So
around.
this object, the bullet cluster, and it gets its name from like a bullet flying through the air and you get that shock front. That's where it came from. This was used as evidence to show that dark matter exists.
Okay.
Because you need dark matter to explain all of the features that you see here, as we've already explained in detail. And so it was put up there on a pedestal as the cluster that kind of shows that, you know, there's other ideas out there like modified Newtonian dynamics, which basically says if you change the force law, so gravity doesn't operate over large distance scales as it operates over much shorter distance scales that we're used to here on Earth, that somehow you can get rid of the need for dark matter.
Right.
And that may be true, right? You'd have to go do the experiments.
Right.
I mean, I can't say. I'm not God. I don't know. But
fact,
I got to do the observations, right?
In fact, MON does fit a lot of the observations,
If you look,
but not all of them.
If you look at, for example, the rotation curve, which is the orbital motion of things going around the center of our galaxy, it actually does a very well.
It does better than dark matter.
Yeah, it does very
really
well.
does.
It does very well at explaining those features. But the thing is I haven't heard yet a good explanation of how you would describe and justify all of the features that you see in the bullet cluster if there was no dark matter.
Right. And that's the problem with MOD.
As far as I know from the MOD supporters, I could be wrong, but as far as I know, that you at least need some bit of dark matter. Well, you either need it or you don't. You can't just say, we only need a fraction of what you need. It doesn't work that way. I'm sorry. Either dark matter exists or it doesn't exist. It's a binary thing, right?
Right.
So if you need dark matter, even if you only need a little bit of it to explain it, you need dark matter. So dark matter has to be there.
Yep.
So that's kind of the status. So James Webb Space Telescope then took a much deeper view, if you like, of this bullet cluster because it is just so important for understanding the ramifications of dark matter. Remember, dark matter is not just a small little bit of pepper on top of the stew. This is a major chunk, right? This is the meat and potatoes part of the meal itself.
Right.
So it really is important to try to understand what the dark matter is. The interesting thing is we've been going down this rabbit hole of trying to detect subatomic particles that would be potentially the dark matter candidate. There's been a number of them. Axions is the latest, greatest thing now. Weakly interacting massive particles, also known as WIMPs. Right?
Yep.
That's another one that people like to use. There's been all kinds of different supersymmetric particles, which we thought would be found by the Large Hadron Collider, which hasn't been the case. Does that mean they don't exist? No. It just means in the area that we search, the parameter space, as we say in physics, there haven't been any discoveries made. So if they do exist, they have different properties than what we're looking for presently.
Right.
So we have to change the way we look, even ultimately to building a different instrument. Who knows, right?
Right.
But so today we haven't, after looking for decades and decades for this dark matter, we haven't been able to discover it yet. And some sense, a part of me is like, yeah, let's not find it yet. Right? Because it becomes more interesting.
It becomes more interesting. It becomes the possibility of new physics.
Yeah.
And that's exciting.
If it would have been something that we could have found many decades ago, it was just another neutrino or some boring particle that someone found. It's like, ho hum, you get used to it. It's like finding the, the Higgs boson. You found it. You knew it should have been there. It was there. Ho hum, let's move on type of thing. Where's the new exciting stuff that no one knew would be there or didn't even predict it, even close to finding? That's what I look for. It's like, hopefully it's something that's just so fantastically different than what we thought, right?
Right.
It's going to amaze and shock everybody and maybe cause a revolution in the way that we understand fundamental physics. That's what I like to see.
Absolutely.
But that's only if I had a vote in the matter, you see?
Yeah.
Which I don't, obviously. Mother Nature does.
Right.
So we haven't found it. Other people, of course, are completely disappointed. They spent a lot of time, effort, labor, money trying to find the dark matter candidate. And so far, nothing.
Nothing.
So even to the point where some people speculate maybe it doesn't exist. And, of course, that question's always in the back of your mind.
Right.
Is it really there?
And in which case, we've got to change our view of gravity in some way.
Something has to give.
Something has to give somewhere. Something is off a little bit in something.
And we're always begging notice for a confrontation with the predictions of the general theory of relativity. Oh, wouldn't we love to prove Einstein wrong, as we say?
We'd love to.
It's all over the internet. You can see that. Einstein was just proven wrong. No,
afraid
that hasn't
not.
happened. A few times we thought we were there, and it turned out to be wrong. One of them, I don't know if you remember this, Rob, just a couple of years back, there was a group in Italy, and of course they don't want to bring this up again, where they had suggested But to be kind to them, they let people know, look, we don't know what's going on here, but it looks like we have neutrinos traveling faster than the speed of light, which is a no-no. You remember that?
I remember that.
Now, we don't know what's happening. We check things, everything, the analysis seems right, the equipment seems to be working. We're going to publish this just to get it out there so people can look for themselves. If you have any ideas at all to help us, we welcome these ideas, because we know that if the result is true, it's a complete upset of physics.
Absolutely.
A complete upset.
Complete.
Yeah.
Physics
you have to
is wrong at that
rewrite
point.
everything in this sense, right?
Yeah.
So what was discovered, that it was a bad cable connecting one of their instruments to the detector, and once that was fixed, the signal went away. The fact that you had particles traveling faster than the speed of light, it turned out to be wrong. So physics was saved because of bad UPS cable, or whatever it was, right? USB cable.
USB cable.
Yeah, or whatever, a coaxial cable or something. So you never know. In other words, if you discover something profound, you better be absolutely sure.
Hey,
Because if you're wrong...
Carl Sagan said it best.
Yes.
Extraordinary claims require extraordinary evidence.
That's right.
It's just the way it is.
And dark matter would be the same. If you claim detection of some kind of dark matter particle or particles, nobody said there's one.
Right.
There could be 2 different types of dark matter particles, or 3 or 4. We don't know.
Right.
Then you better be sure. And how do you sure it? Well, someone else needs to do an experiment to see if they detect it with the same properties that you think it has. And if you don't see it, then does it exist? It doesn't.
It doesn't.
You do these experiments, you can't find it. Only you were the one that found it. And we've had that situations in the past where somebody's detector went off and nobody was able to reproduce those observations, so it's not a detection.
It's not a detection.
In physics, you'd have to be able to run the experiment, get the same result over and over and over and over again before it's accepted as fact. That's the way science works. So, well, who knows how long it might take to know what the dark matter particle exists or not, but we know there's some form of matter out there
that we can't see.
That doesn't give off light. And we checked all the different wavelengths and frequencies. You checked in the infrared, you checked in the radio, you checked in the X-rays, the ultraviolet, the infrared, you name it. It's not there. But, and
its
you might say,
gravitational effect
right,
can be
because
seen.
you might say, well, then how do you know it's even there? Is because it affects things that you can see via gravity.
Right.
So you disturb the orbital motion of things in galaxies because of dark matter. You disturb space and therefore cause gravitational lensing like a nebula cluster due to the gravitational interaction of the dark matter.
Right.
So we know it's there indirectly due to its gravitational influence on the environment around itself.
Now it's just a question of kind of like the earlier TWA-7b. Now it's a matter of finding the direct evidence.
Right. And if you never find it, well, then what's causing the gravitational effects of the stuff, right?
Right.
There has to be some explanation for that. And that's where you alluded to already. You go down this hole of thinking, well, then gravity needs to be modified.
Right.
But we have a lot of tight constraints on gravity in different experiments. We know gravitational waves exist. All of that would have to be supported by any new ideas of gravity that we have.
Yep.
And that seems like a huge enterprise to go through.
I mean, it's over 100 years now, and general relativity has stood up to every test. So,
yeah, exactly. So that's
GR is pretty solid, folks.
Pretty solid. Now, of course, you can get involved in all of this, especially if you're a young person just starting out. Maybe you're in high school and want to figure out what to do in life. Go on to higher education to learn in depth about physics and mathematics and explore these topics that are so important today in fundamental physics.
Or if you want to communicate these to the public and otherwise, come to higher education.
Yeah, and one way you can do that, of course, is come here, like the University of North Dakota. We have lots of courses that you can take both on campus and online.
Yep.
And we have wonderful programs both in mathematics and in physics and in English and in different programs in aviation and so on. So there's lots of things that hopefully you'll find something that's your calling that you can choose from.
Heck, public policy, so you can help determine the funding for some of these
All
things.
of this stuff is extremely important. And even if you just want to educate yourself,
right?
An educator voter is probably the most powerful person in a democracy. And that becomes extremely important at critical times, as we know so often at recent times, how important that is. So getting out there and learning, be a lifelong learner.
Absolutely.
For sure. Now, our next podcast we'll have a week from now, so that would be July the 8th at the same great time at 5 p.m. And we always leave you with a quote at the end of our podcast. Today's quote is actually from somebody that we talked about at great length today, Nancy Grace Roman.
Okay.
So Nancy Grace Roman, who was born in 1925, she passed away, unfortunately, in 2018. Well, she lived a good life. I wish
Absolutely.
I could live that long as well, hopefully. And in good health. That's important as well.
That's important.
As I noted, that she was sort of the first in her era to become at a high position in administration at NASA, to be the chief astronomer in that sense of the running of the agency. And the quote here is related to her work at NASA. So here's the quote. I've had never used the prefix doctor with my name, but when I started with NASA, I had to. Otherwise, I could not get past the secretaries.
Wow. That's a shame.
Yeah. But don't forget, this is
1959. Yeah.
So that was a different world back then, as we all know, than what it is today.
Yes.
And the only thing is, it may be different, but hopefully it's better today.
Hopefully it's better.
That's what we strive for. Anyways, if you like this podcast, please don't forget to give us a thumbs up. Subscribe to the channel if you haven't subscribed already. And please join us another time.
Absolutely.
And thank you very much for watching.
Thank you, folks. You have a good day.